Greetings from smoky Stanford. It's too smoky and too hot to sit outside to do this little tutorial on risk. So we're going to do it inside today. Where we last left off, I was talking about risk aversion and its definition in terms of the curvature of the fitness function. So let's think a little bit more about how the degree of curvature of the fitness function affects the degree of risk aversion. Share my screen. And we'll draw some axes here. As usual, we have the outcome of our decision. We have the fitness function that's associated with the outcome. And we have concave fitness function this time. And let's call this one F1 this time, because we're going to draw two of them. The second one is going to look like this. We'll call that one F2. Note that they start and end at the same place. So they're going to have the same value of x bar here, and they're both going to have the same mean fitness. However, we can extend this line up a bit. Draw these back to the y-axis. So that the fitness of function 2 with respect to the mean outcome is quite a bit higher than fitness 1 with respect to the mean. Notice that F2 is much more curved. It accelerates faster and then it flattens out sooner than F1, okay? So what does that mean? If we play one of our gambles at, say, this spot here versus here on curve 1, right, the asymmetry between the upside risk and the downside risk, while it's asymmetrical, it's not going to be as asymmetrical as the asymmetry between the upside risk. Oops, that's a little too far. And the downside risk. Although, honestly, where I've drawn it, it's actually flattened out so much already that it doesn't actually matter that much. If we were to do it here, we'd see that there was an enormous asymmetry, difference in asymmetry. Okay, so what does this mean for the willingness to pay for certainty? Okay, that's the certainty premium, and we can figure out what the certainty premium is by figuring out where this line that goes back to the y-axis from this this line segment that connects mean fitness. I'm sorry, not mean fitness, the mean outcome with the curves. Take that back to the y-axis, right? And where it crosses the fitness curves, F1 and F2, that's going to tell us where I change the color. It's going to tell us the location, therefore the magnitude of these certainty equivalents. So X sub C and A1, X sub C 2. All right, so there's pi 1. And there's pi 2. The certainty premium is much bigger in the more curved fitness curve, right? Because the asymmetry, particularly early on here where it's most curved is going to be steepest there, right? The upside and the downside risk are going to have the biggest asymmetry between them. This means that if you're playing this highly curved gamble, you should be willing to pay more for certainty. And that's exactly what this difference in the certainty premia is capturing. Okay, so this basically tells us that you are more risk averse the more curved your fitness or utility function is. Okay, and there's a measure that was independently created by two economists, Ken Arrow from Stanford, John Pratt from Harvard. And they basically noted that this curvature it determines risk aversion, but they also noted that the way economists define utility functions, they're only defined uniquely up to an affine transform. And so you have to actually alter them a little bit. So the obvious choice would be a second derivative, right? Because that measures the curvature of a function. But the so-called Arrow-Pratt index of absolute risk aversion, the Arrow-Pratt index absolute risk aversion, and we'll indicate that A sub F, F being fitness, A being aversion, arrow, I don't know. When it's defined for a utility function, it's usually denoted A sub U, but we're working with fitness, so we'll call it A sub F, is defined as minus the second derivative of our fitness function divided by the first derivative of our fitness function. And that accounts for that, that fact that these functions are defined, at least in economics, only up to an affine transformation. By dividing through by the first derivative, you scale it so that you get a unique value for any specific second derivative. And it turns out that this is actually mathematically very convenient. It pops up repeatedly. And we're about to see how it pops up in another measure. All right, so this is the Arrow-Pratt index of absolute risk aversion. It's essentially a scaled measure of the curvature of our fitness function. All right, so the next question we want to ask is, we've seen how much you should be willing to pay for certainty. That's the certainty premium, and if that's a function of the curvature of our fitness function. The question is, can we come up with some sort of analytical insight into how big this risk premium should be given a certain curvature and given a certain amount of variability? Naturally, the answer is yes. And what we're going to do is we are going to define a random variable, epsilon, okay, that has a mean, or 0, and a variance we'll call sigma squared. All right. And this is a little bit of trickery, perhaps. We're going to equate the expected value of our fitness function plus this random variable with the fitness function minus of a payoff minus the certainty premium. And the reason we're equating these two things is that if you somehow force a decision maker who would rather have a certain payoff to nonetheless play a lottery, what you're doing is you're penalizing them the amount that they would have paid for certainty. Okay, so that's where this equality comes from. This is the left-hand side here is the expected value of the lottery, and this is the penalty that you pay for having to play a lottery when you prefer to get a certain value that you've paid a certainty premium for. Okay, and the way we're going to gain some analytical insight on this is we're going to do another set of Taylor series expansions. And this may seem a little magical, I don't know. On this side, we're going to do a second order Taylor series. And on this side, we're going to do a first order Taylor series. Why is that? Well, I mean, on the left-hand side, we've got an expectation. On the right-hand side, we don't have an expectation. And so when you do a first order Taylor series, you're really just looking at the tangent of the curve. And you're imagining you're in a fairly small range of perturbation around there. And so, but when you've got an expectation, you probably need to account for at least the variance, right? So we need to think about doing an expansion that goes up at least until the second order, okay? That's the best explanation I could come up with. So we've got an expectation of fitness of x plus epsilon times the first derivative plus epsilon squared over 2 times the second derivative. And we'll set that equal to, this time it's a first order Taylor series, f of x, not plus, minus, because it's x minus pi times f prime x. So the linear approximation of the fitness curve in that vicinity. Okay. So as with our previous derivations, taking the expectation of this first order term, right, is 0, because it ends up taking, subtracting a mean from itself, and that's 0. Okay. The expectation squared, and note that our mean is 0. So this is like saying this is epsilon minus the mean squared. So that's a variance, right? So variance of x. Okay, that's good. So let's just rewrite this. So now we have f of x, because the expectation of just a number, right? F of x is just one number, so its expectation is itself. 0 plus f prime of x, variance of x over 2 equals f of x minus pi times f prime of x. All right, so we've got f of x on both sides of the equation, so those cancel out. We want to isolate pi. We're trying to estimate what the certainty premium you'd be willing to pay for a given fitness function should be. So we need to divide here by minus f prime of x. Okay, so we'll just do that. F prime of x, and then we'll make that minus. All right, now we can neaten it up a little bit. Pi equals minus f prime of x over f prime of x times the variance of x over 2. And we should recognize what this first term is, f prime x minus f prime x over f prime of x is the Arrow-Pratt index. I said it was mathematically convenient to normalize it by that first derivative. And so we can rewrite it in the form you usually see it as, we'll call it A of f. That's our Arrow-Pratt index for the fitness function f. Sigma squared, right, because the variance of our random variable is sigma squared over 2. Okay, so this gives us, and this only works for small variations near this value of the mean. Okay, that's pretty important because we've done just this linear approximation of the penalty that you pay for being forced to play the lottery, right? But what it tells us is that the curvature is going to determine in large measure our certainty premium, but then so is the variance, right? So the more variable, so the bigger the distance between the high and the low for a gamble that involves two outcomes, right? The more variable it is, the more risk averse you are. The greater the curvature, as measured through the Arrow-Pratt index, the more risk averse you are. And those both enter linearly, at least for these small approximations. So I hope that these three videos, tutorial videos on risk and risk aversion, the calculus of risk have been useful. Got more on the way. Thanks.